Hashing is the process of converting a given input, such as a key or string of characters, into a fixed size value, typically a shorter representation known as a hash value or hash. This transformation makes it easier to identify, locate, or reference the original data efficiently, without storing it in full. One of the most common applications of hashing is in the creation of hash tables, which store data as key-value pairs. In a hash table, the hash function maps each key to an index in the table, allowing for fast data retrieval. Since the potential number of keys can be vast, the hash function ensures they are evenly distributed across a finite table size, minimizing collisions and improving lookup performance. A hash function is responsible for generating these hash values based on a mathematical algorithm. A key feature of a strong hash function is that it is one-way, meaning it is computationally infeasible to reverse the hash value back to its original input. This one-way nature is essential for maintaining security and data integrity. Hashing plays a crucial role across various fields, including data indexing, cryptography, cybersecurity, and digital signatures, where it helps ensure the integrity, authenticity, and efficient processing of information. How hashing works. 1. Input. The input refers to the data fed into a hashing algorithm. This data can be of any type or length, ranging from a simple text string to a large file such as a document or an audio track. Regardless of its size or format, the entire input is processed to generate a single, consistent hash output. 2. Hash function. At the core of the hashing process is the hash function, which performs a series of mathematical operations on the input data. This function transforms the input into a fixed-length string of characters, known as the hash value. A key property of hash functions is their sensitivity to input changes. Even a tiny modification in the input will result in a drastically different output. This ensures data integrity and makes tampering easily detectable. 3. Hash output, hash value. The output of the hashing process, also called a hash value, is always of a fixed length, regardless of the original input size. This consistent output length makes it difficult to determine the original input, enhancing security. Since the output appears as a unique string of characters and numbers, it effectively serves as a digital fingerprint of the input data. This uniqueness helps protect sensitive information, as hash values are not reversible or human-readable, making unauthorized access or interpretation extremely difficult. Key properties of hashing. Deterministic. A hash function must consistently produce the same output for the same input. Fixed output length. A hash function should always produce an output of consistent, predetermined length, no matter how large or small the input data is. Fast computation. The function should compute the hash value rapidly, ensuring quick processing even for large amounts of data. Pre-image resistance. It should be practically impossible to determine the original input from a given hash value, ensuring one-way security. Collision resistance. It should be extremely difficult to find two distinct inputs that generate the same hash output. Avalanche effect. Even a minor change in the input should result in a drastically different hash value, reinforcing unpredictability and data integrity. Hashing algorithms. MD5. Output. 128 bits. Status. Broken. MD5 was once widely adopted for checksums and digital fingerprints. However, it is no longer cryptographically secure. Practical collision attacks have been demonstrated, Wang et al., 2004, and further optimized, Mark Stevens, 2012. Avoid use in all security-sensitive contexts. SHA-1. Output. 160 bits. Status. Broken. Although more secure than MD5, SHA-1 has known collision vulnerabilities. The Shattered attack, Google and CWI, 2017, demonstrated a real-world collision, proving that SHA-1 is unsafe for digital signatures or authentication. SHA-2 family. Output. 224 to 512 bits. Status. Secure. Includes SHA-224, SHA-256, SHA-384, SHA-512, SHA-512, 224, SHA-512 256. SHA-2 remains the industry standard. It is used in SSL, TLS, digital signatures, e.g., ECDSA, blockchain systems, e.g., Bitcoin, and software integrity verification. SHA-3, KEKIC, output, 224 to 512 bits plus SHAKE XOFs. Status. secure, and designed to be resistant to new attack classes. Based on a new structure, Sponge. Unlike SHA-2, SHA-3 is not a direct successor but a complement. Uses Keccak F permutations on a 1600-bit state. Applications of hashing. Data integrity. Data integrity is one of the most common uses of hashing. By generating a hash value for a file or message before transmission, users can later compare it to the hash of the received data to check for any alterations or corruption. If the hash values match, it confirms that the data remained intact and unmodified during transfer. Efficient data retrieval. Hashing significantly improves data retrieval efficiency, especially when working with large datasets. By using hashing functions or algorithms, data is mapped to a corresponding integer value, which acts as a reference point for quickly locating the item within the dataset. For instance, in hash tables, data such as customer records is stored as key-value pairs. The key serves as an identifier for the data and is processed through the hash function to generate a hash code, integer, which is then mapped to a fixed size location. Common operations supported by hash tables include inserting key value pairs, retrieving key values, and deleting key entries, all of which benefit from the fast access enabled by hashing. Digital signatures. Hashing plays a crucial role in authenticating digital communications by enabling the secure use of digital signatures. In this process, a hash function is applied to a message to generate a fixed-length output known as a message digest. This digest is then encrypted with the sender's private key to create the digital signature. The original message and the digital signature are transmitted separately to the recipient. Upon receipt, the recipient applies the same hash function to the message and decrypts the signature using the sender's public key to retrieve the original digest. If both digests match, it verifies the message's authenticity and integrity. This process ensures that the message has not been tampered with and confirms the identity of the sender. Password storage. Hashing is also a standard method for securely storing passwords. Instead of saving passwords in plain text, systems hash them and store only the resulting hash values. This approach significantly enhances security. If an attacker gains access to the hashed data, it is computationally impractical to reverse the hash and obtain the original password, especially when additional techniques like salting are used. Blockchain technology. Hashing is a fundamental component of blockchain technology, particularly in cryptocurrencies like Bitcoin. A blockchain is a decentralized digital ledger that records transaction data, with each new transaction being added as a block. Since all participants in a blockchain network have access to the same data, maintaining the integrity of previous transactions is essential. Hashing ensures this by safeguarding the immutability and accuracy of the data stored within each block, making it nearly impossible to alter past records without detection.